Welcome to week 8. This week we're going to talk about optimization and efficiency. The main topics for this short lecture are to define the two types of efficiency. One is just the process or flow of materials to make a product. And the other is the total material and life cycle, that is all the machinery and energy that it takes to create a product. So we're going to look at examples of house construction to look at sort of a simple example of optimization and why we might strive for efficiency. And then I'm also going to present a method to look at multiple unit efficiency, where you have an optimum for each component, but you can't really make a trade-off between those two components that you're trying to manage. And in this case, it's going to be biodiversity versus economic development in the Willamette Valley. And then finally, we're going to discuss why efficiency, just on its own, shouldn't be the goal. It can be a method by which you get to reducing energy or reducing costs, but the goal really has to be improved quality of life for humans or improved biodiversity. That's really the goal, and just efficiency might be too short-sighted. So, first of all, these two definitions. The first, process efficiency, is simply where we have how much products are produced for how much inputs are coming in. And it's a very simple ratio of the products over the total inputs. And for example, it might be something like usable energy over energy input on a fireplace. How much energy as wood did you put in? How much energy did you get back into the room as heat? We often see this in energy efficient appliances. How much energy did it take in terms of electricity to run your water heater, and how much hot water did you get? So what's the efficiency of that? It's just based on the energy used to how much is going to be available. Now, another way we've seen this is what's the weight gain of a turkey or some other animal compared to the total food input. This is very seasonally interesting because turkeys gain weight really quickly, and that's one of the advantages of turkey as a food. Another more complicated that we're going to study more in Environmental Science 102 is what's the water efficiency for crops? That is, how much crop do you get for the total amount of water you use for irrigation? That would include losses to bad pipes, evaporation during the irrigation process, and just the growth efficiency of the plant itself. Now, the total materials and energy efficiency is just sort of taking a bigger scale look at that same issue. So we might have, what's the production rate based on all of the products, the total machinery, or all of the costs that it took to create something. So the wood stove example would be, how much heat do you get into the room compared to the amount of wood, how much energy it took to transport, store, cut the wood, grow the wood. So if you were cutting down trees and used a chainsaw and a truck and a tractor to get your wood over to your house, how much energy did you really get out based on all of that effort? So it's much more complicated, and we're going to look at that sort of concept a lot more in ESM 102 when we look at a counting method called life cycle analysis. And again, the same sort of thing, comparing for a turkey. What's the weight gain of a turkey compared to the food costs, the water, the buildings, the heat for the buildings, the medical care, all of those things that it takes to raise a turkey up to bringing it to market. So first, let's look at process efficiency, and we've seen this before when we looked at metabolism of an organism. We looked at a diagram of a deer growing and how much energy was in the food it ate and where that energy went. And if that energy went to energy stored as new growth, then the efficiency was just how much energy was in the new growth, the new biomass that the deer was putting on compared to how much it ate. And we saw that the waste was a combination of things such as the amount of food that was metabolized to CO2 went off into the air, the amount of food that was indigestible because it's maybe twigs and other things, and then the amount of food that was just went through the organism was was digested but wasn't quite captured. So all of those would be in this waste energy category. And it's important for us to remember right now that this waste is part of the inefficiency for a deer growing, but it might not be waste as far as the ecosystem is concerned. For example, deer feces, very important for the microbial components of the soil. Those microbes live off that. Those microbes live off that as their food. So, looking at the total materials approach, let's take the example where we have two processes, process A and process B. Each of these processes requires some sort of machinery, and then that machinery for running the process has a particular factor of its own efficiency. Now, these processes might be things like machines on a factory floor, or they might be the components in a biological system, such as, you might have a certain amount of stomach and a certain amount of lungs, and you got to balance those. And the idea for this is that the potential output of each process contributes to the overall formation of the product, but what's going to limit the rate of that formation of product is whichever process goes more slowly, whichever is rate limiting. So, in this example that I'm showing here, which I'm hoping will also be available as a simulation under the simulation link, we're going to look at the total material efficiency is the rate of product over the total machinery for A and the total machinery for B added together. And in this particular example, we're going to see what happens for the potential output if you need twice as much A as you do for B. So what that means is if process A is running twice as fast as process B, then both of them are limiting the rate equally, and that will determine the final formation of product. But if process A is the same speed as process B, then process A will be limiting it, and process B will be going twice as fast as it needs to be, because remember, you need 2 times as much A as B. So in that case, when you have a process B that's potentially faster, you don't need as much machinery to run that. And so the system can become more efficient by having less process B machinery. So to put it in another word, if you have these two processes and whichever one's limiting the formation of product, then you should add more machinery to that. That'll speed up the rate of formation of product. But if you add too much, it just ends up being extra machinery, and it'll decrease the overall efficiency by making that unused machinery, so to speak. So again, we're taking a very mechanistic view of this, but there's so many in this idea of efficiency and optimization. It is a very mechanistic approach to looking at problems. Okay, let's shift gears a little bit and look at the total energy budget for a house. And this is a comparison study where 2 single-family homes were designed, and they kept track of all the materials that would go into building those houses and how much energy it would cost to operate those houses over a 50-year lifetime. So they were single-family homes, looking at this diagram, the picture to the right, sort of simple construction, nothing really exorbitant. And what they found is that during the use phase of the home, that is actually living in it, not the building or tearing it down, accounted for 91% of the life cycle energy. And in the energy efficient home, it used 156 kilowatts per meter square of house per year, and the standard home construction required about twice as much energy per year. So that's really the difference between these two homes, is like, what's the operation cost? But when they built them, there was more energy required to build the energy efficient home, and we call that the embedded energy. They used more wood because they made the walls thicker. They had more metal and cost in appliances because they bought better appliances that were more energy efficient. And they used a lot more concrete in the building of it so they could have a substantial foundation that actually insulated the house better from the ground. But even then, even though they used all those extra materials, the overall impact was that the life cycle CO2 for the energy efficient home was 370 metric tons over its lifespan, and the traditional construction, that is the low energy efficiency, was almost 3 times that at 1,000 metric tons. So in this case, building a simple home, it cost more to build the energy efficient home, required more materials, but over this long life cycle, it really paid off. Now, let's look at one that isn't quite so clear cut, which is energy for a home in a cold climate. And this study was done by comparing the construction of 2 types of homes. One is a sort of a traditional Japanese home, and this is in Hokkaido, so cold weather climate of northern Japan, compared to a vertically integrated house, meaning it was constructed at a factory and shipped to the site. And the vertically integrated home was smaller and better insulated, and it required 59% higher energy per meter squared to build. And it had, over the period of time, had 17% lower energy use. But this vertically integrated house also had more residents per meter squared, and this comes from sort of the neighborhoods where these were built. They had maybe grandparents living with them, or they had some other little larger family. So it's really sort of a hard thing to compare when you've got like sort of bigger home with fewer residents and a smaller, more compact home with more residents. So the other thing is that the CO2 emissions, which I'm not going to go into here, but they're very complicated about where they sourced the material and how they could save the CO2 emissions on all aspects of the construction, because in Japan, the companies that can save CO2 emissions are eligible for tax breaks and subsidies from the government because of CO2 emissions. Okay, now I'm going to talk about a process that we can use to optimize for multiple variables. So the example here is land use planning in Oregon, and we're trying to develop the urban and economic zones up and down the Willamette Valley. We're also trying to preserve landscape that promotes biodiversity. So it's really hard to compare the dollars that come from economic development to biodiversity. But what we can compare is, and this study did this, is what are the patterns on the landscape that would be better for biodiversity and how much area do they take up? And that includes looking at farm use, forest use, industrial and urban uses. And then we can determine from sort of any particular amount of area devoted to biodiversity, what's the maximum biodiversity protection that you could get. So you have a certain amount dedicated to development, a certain amount dedicated to biodiversity, and by rearranging the land use patterns, you can get high biodiversity. So you're not trading off dollars directly for biodiversity. You're looking at both of them at the same time. When you do that, you come out with this diagram. I'm going to explain this optimization curve. Over the top left, you have where you see the little diagram of the Willamette Valley. It's almost all green. You get the highest biodiversity with expected number of species at 257. So this is all done by simulation modeling. And then as you move to the right and down over to the bottom, when you're over at the bottom, you see the bottom right, you see the least number of species but the highest development cost. And there's a lot of urban areas, there's a lot of rural residential, a lot of managed forestry, and that ends up being, the sort of how you can make the most money. But anywhere under the curve could be improved. So for example, the point I that's in the middle, it's as close to the land use pattern we have now in the Willamette Valley. If you moved it to the right, you'd get the same amount of species, but more development, more development dollars. And if you moved it up, you'd have the same amount of development dollars, but the same, but much more biodiversity. So you see, you can move toward this optimization curve from anywhere in the middle. You can move toward the optimization curve and improve both the number of species and the dollars from development. So this is a very powerful way to look at trading off two different components that you're interested in. In this case, preserving number of species, but yet still providing economic development dollars. Okay, now, as I said in the beginning, I want to make sure we understand that efficiency isn't the goal. So what's the purpose of striving for efficiency? And we often hear this: if all other factors are the same, we should have higher efficiency cars or something like that. Well, it's almost never the case that all other factors are the same. So we need to consider what those factors are. If we're going to take a multiple perspective approach to these problems, we need to say, well, what are those factors? If we make cars more efficient, people just drive more, how did that get us anything? Or if you have a potato chip factory that's more efficient, well, what did that really get us? It got us lower energy wasting on making potato chips, but was that really a social and environmental goal that we wanted to go for in the first place? So here's a good example of why we have to also examine the waste. Now, if you look at, here's the total number of trees, and then here's how much lumber is used in building as the process. Well, trees that fall to the forest floor, they nurture the ecosystem. Sawdust on the mill floor becomes a waste that you'd want to reduce that amount of waste, and it really doesn't go to too many useful uses, although it's being used for biomass power. And then the worst of these three is defective wood products that went already to the consumers. That stuff has to be thrown away and replaced. So it's actually, like twice as bad as just reducing the amount of waste in the first place. So each one of these is a type of waste, but that waste has very different impacts on the ecology and the economy. So we want to be very clear about what we mean by waste in the forest products industry. Is it dead trees on the ground in the ecosystem? Is it some side product that can't be used efficiently, or is that actually defective products at the end of the pipe, which would be very, very costly and very damaging? The other part about excess capacity is that we see if everything was tuned to be totally efficient, you wouldn't have any excess capacity to meet temporary fluctuations in demand or the ability to respond quickly to new opportunities. So just trying to develop a system that works for optimal efficiency, narrowly defined at any one time, really can be short-sighted again. All right, now in the house examples, just to review, the energy in the energy efficient house comparison, we could save money in carbon emissions, but again, we had to look at the total site and use. So for example, in the comparison of two homes that could have been built in the United States, they didn't consider at all landscaping, like could they put trees around there, or the size of the home, or the usability of the space inside the home. Those are things that probably other studies have looked at. But again, for the use of the house by a family, these other things might be very effective as well. And they were left out of that study. I'm not complaining about that study. I'm just saying it's a limited approach. And in the cold climate house example, the social aspects of how those homes were used was very important. Where they were located, how people got around. That in turn really drove the sort of comfort and usability of those homes. In the biodiversity versus development example, we have good planning could promote both factors. Problem is, once you've already gone past sort of some planning horizons where you've already built roads and industries in certain areas, it's very difficult and expensive to go back. But the idea is still there that you can have different types of land use. And the real advantage of that was you didn't have to make a conversion factor because they relied on these simulation models that showed what could happen. They didn't have to rely on just an economic conversion factor where each bird is worth so many dollars. That really gets into a downward spiral that devalues all of the potential benefits of biodiversity by just placing it in terms of money. So in conclusions, we have the two different types of efficiency. We understand that too much waste or production capacity decreases the efficiency, but we saw those maybe that is waste and excess production efficiency might be desirable in some situations. In the example of the homes, the assumptions are very important, but it's a good exercise to look at building energy efficient homes, and along with other factors, landscaping, siting, proximity to services, those sorts of things. And in the biodiversity versus development example, it demonstrated a model to look at multiple factors without having to reduce it all to dollars. And finally, we had a short discussion on why efficiency shouldn't just be the goal. We need to examine human values in order to choose the solutions, but that we need to use those analytical techniques to try to increase the efficiency and decrease investments that aren't going to be useful.